Assalamu alaikum everyone. This is Abdul Qadir Goni and I welcome you all in my A-level physics classroom. Today we are going to study electric fields. This is the second part of electric fields and the first part has already been uploaded in YouTube. You can check it there. And this is the second part. Before watching this lecture, I suggest you to watch the first part before the second part. Okay, and in this part of the video we'll be discussing about these contents on this topic. So the first we'll be discussing about Coulomb's law, then we'll make you understand about radial field calculation, we'll make you understand a work example about levitation, and two experiments. One experiment involving verification of Coulomb's law and another one is Millikan oil drop experiment that he did to find out the charge on an electron. Okay, without wasting any time, let's get started. First, we are going to study Coulomb's law. Before stating the law, I want you to understand what actually the law means. For example, we are considering two charged objects placing at a separation two charged particle or two charged objects with a separation r between them, and one object or one particle has charge q1 and another one has a charge of q2. These two objects may be sphere, hollow sphere or solid sphere, or they can be two charged particles, for example two electrons or one electron and a proton or two protons, or two oil drops. Okay, two oil drops. So here is a particle or object having a charge q1 and this is another charged particle or charged object having a charge q2, and they have a separation r in between. Okay, and we know that like charges repel and unlike charges attract. If the two particles or two objects have like charge, they will repel each other, and if they have opposite charges, they will attract each other like this. So there may be force of attraction or repulsion, and this force of attraction or repulsion is due to the charge. That means it is an electrostatic force of attraction or repulsion. And you have to remember that the greater the charge on the objects or particles, the greater the force of attraction or repulsion. I'm repeating, the attraction, whether it will be attractive or repulsive, that will depend on the sign of the charges on the objects. Okay, so the force between them will be proportional to the product of their charges. Okay, the larger the charge on either one or both, the product will be larger, therefore the greater the force of attraction or repulsion will be. And the further they are separated, the smaller the force of attraction will be. Okay, so the force of attraction or repulsion will be inversely proportional to the square of the separation between them. And while doing calculation, you have to consider the separation from center to center, whether it is a hollow object or hollow sphere or solid sphere. Okay, from center to center, and the force acts between the centers, whether it is attractive or repulsive. And combining these two, we can write F is proportional to Q1 Q2 by R square. This is actually Coulomb's law. Okay, so what Coulomb's law states? Coulomb's law states that the force of attraction or repulsion, or specifically the electrostatic force of attraction or repulsion is directly proportional to the product of the charges and inversely proportional to the square of the separation between them. Okay, so this is the Coulomb's law, and it states that the electrostatic force of attraction or repulsion between two charged objects or two charged particles is directly proportional to the product of their charges and inversely proportional to the square of the separation between them. Okay, and if you want to make an equation, F is equal to K Q1 Q2 by R square. Here K is a constant, and by doing calculation the constant will have a value of F, and this constant K is equal to 1 divided by 4 pi epsilon. Okay, this is a Greek letter and has the pronunciation epsilon. Okay, this is epsilon, and this epsilon here stands for the permittivity of the medium. Permittivity of the medium. So by removing K, we can write 1 by 4 pi epsilon into Q1 Q2 by R square. So E or epsilon is the permittivity. Epsilon, this stands for permittivity. So what is the permittivity? Permittivity stands for a medium in which the force of attraction or repulsion is acting, and the force of attraction or repulsion is acting because of an electric field produced for the charges on the objects. Okay, so permittivity is a measure of how easy it is for electric field to pass through the medium. So it is different for different media. Okay, so permittivity is defined for particular media. So permittivity of a particular medium is defined as how easy, or permittivity of a particular medium is defined as a measure of how easy it is for an electric field to pass through that medium. Okay, therefore we can write 1 by 4 epsilon Q1 Q2 by R square, and if the two charged object or two charged particles are placed in vacuum or free space, then we can write F is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. Epsilon naught represents not 0, that means no medium there. Okay, so epsilon naught stands for or represents the permittivity of free space. Permittivity of free space. And while doing calculation, air is considered to be free space. So when we are doing calculation, if the particles or objects are placed in air, the medium in which they are placed, then considering air to be a free space, we'll use this equation. And this is a constant, and calculation showed that K, when it is 1 by 4 pi epsilon naught, is equal to 8.99 into 10 to the power 9 Newton meter square per Coulomb square. Okay, 8.99 into 10 to the power 9 Newton meter square per Coulomb square for free space. And in your Edexcel IAL syllabus, you will consider this. And you can also write it simply 9 into 10 to the power 9. Okay. So this is the Coulomb's law, and from the formula we can find out whether the force will be attractive or repulsive. Look at the diagram and the formula. If Q1 is positive and Q2 is negative, then Q1 positive, Q2 negative. So there will be a negative sign. The product will have a negative sign that shows the force is attractive. Negative sign stands for attractive forces. And if they both have positive charge, therefore plus plus, and result will be a positive there, and it shows that the force will be repulsive. If both of them have negative charges and negative negative, and the product will be still again positive, therefore this shows the force is repulsive. And from this equation we can find out that the force will be an attractive if the charges are opposite, and will be a repulsive force when the objects or particles have similar charge or like charges. Now, radial field calculation. Suppose this is a particle or object having a charge Q1 and it's positive. Okay, it's positive, and this will be the electric field, and the field lines showing outwards. Okay, this is radial field or an electric field, radial electric field produced by a charge Q1, and this is the electric field. And suppose you have brought another particle Q2 charge having a charge Q2, another particle, another object that has a charge Q2 on it, and consider this is also positive. Okay, so the charge or the charge particle will be repelled by this one, so it will experience a force F in this direction, and we can consider it F Coulomb force. And suppose the particle is a distance r from the Q1 charge. Okay, so this is an electric field, radial electric field produced for Q1 charge, and Q2 another charge particle that has been brought into the field produced by Q1, and Q2 is experiencing a force. If Q2 is negative, then the direction of the force will be in towards the Q1. This is the difference between a positive and negative one, and the direction of force depends on the sign of the charge, but the size of the force depends on the distance, that means the separation and the product of the charges. And this is F Coulomb, and for this we can write the equation Coulomb force, and if the electric field strength is E, we know electric field strength of this field at this point, okay, at this point, or the electric field strength of Q1 at a distance r from its center, that is E is equal to, we know, F divided by Q2. Okay, F divided by Q2. I think you remember the formula of the electric field strength. E is equal to F divided by Q, electric field strength, force on unit charge. Okay, so if Q charge experiences a force F, then per Coulomb charge experiences a force of F by Q, and by definition this is the electric field strength. So if Q2 charge experiences a force F Coulomb, then unit Coulomb charge or per Coulomb charge will experience a force of F Coulomb divided by Q2. And now we have the formula of Coulomb force, K Q1 Q2 divided by R square divided by this Q2. and we can cancel this Q2 and Q2. So we'll have the formula K Q1 divided by R square, or you can also write 1 by 4 pi epsilon Q by R square, sorry, Q1 by R square. And if you want to write a general equation for the electric field strength of a radial field, if we consider, okay, look at the equation. Q1 is the charge of the object for which the field is produced. So therefore we can write, if an object has a charge Q, and at a distance r from the charge, or from the center of the charge, we can write this equation or modify this equation. E is equal to 1 by 4 pi epsilon into Q by R square. Okay, this is the equation or general equation for electric field. Now you can also write simply K is equal to K Q divided by R square. Okay, so electric field strength at a particular point of a field or radial field. Okay, this is the equation for the electric field strength, and from this equation we can see that the electric field strength at a distance r from the center of the electric field, and the electric field produced for charge Q will be E is equal to K Q by R square. And this is the final general equation for electric field strength of a radial field. So now we are going to deduce another formula for electric potential. Suppose now we have found out the field strength equation. Now you want to find out the electric potential. Okay, electric potential, and we know that in radial field, electric field strength actually is a measure of how quickly electric potential varies. Electric potential varies is dV by dx. Okay, in a radial field, electric field strength will be a measure of how quickly the electric potential V varies. So you can write the equation E is equal to dV by dx, and this leads to an expression for the electric potential. V is equal to KQ divided by R. Okay, you can also write 1 by 4 pi epsilon into Q by R. Okay, so this is the equation for electric potential. Now we are going to understand and work example in your book about levitation. Before starting the calculation, let's understand why do we levitate. Okay, suppose this is the surface of the floor, and the surface must be made of atoms like this, and the center of the atom is positively charged, which is the nucleus, and electrons are orbiting around the nucleus. So the outer part of the atoms will contain electrons. Okay, so the upper part of the surface will have a sheet of electrons, we can consider, or we can say that the upper part of the surface will have a skin or a sheet or a layer of electrons on it. Okay, and same thing, and there is also electrons. Okay, since the outer part of any atom is actually occupied by negatively charged electrons, and same thing is true for your foot or your shoe surface, your bottom surface of the shoe. Suppose this is the bottom surface of your shoe. This is also made of atoms, and this also has electrons like this. So these are like charges. Okay, electron and electron, like charges repel each other. So there will be a force of repulsion. This will repel this and this direction. Therefore, there will be an electrostatic force of repulsion between the two surfaces, which makes you levitate. And now we are going to find out the amount of levitation, or how high we actually levitate. And for this, we have estimated some data. Okay. For example, so we are estimating the height at which a person levitates. Okay, we are estimating the height at which a person levitates, and for this we have taken some estimation, and suppose an estimate of the person's weight, okay, is 800 Newton, and estimate of shoe surface 10 centimeter by 30 centimeter. Okay, then another estimation of the radius of atom, estimate of the radius of atom 1.5 into 10 to the power minus 10 meter. Okay, these are the estimation. We are estimating the weight of a person, about 800 Newton. The shoe surface is 10 centimeter by 30 centimeter, and the radius of each atom is about 1.5 into 10 to the minus 10 meter. Okay, so when we are standing on a surface, our weight is distributed in two legs. So each leg is supporting half of the weight. Therefore, each shoe in this case is supporting half of the weight of the person. So now we are going to solve it. So force on one shoe, or force supported by each shoe, will be 800 divided by 2, and this will be 400 Newton. Okay, now let's find out the area of the shoe. Okay, then the area of the shoe in contact will be 10 centimeter by 30 centimeter. So converting them into meter, 0.1 into 0.3, and this will be 0.03 meter square. Now area of the shoe, and suppose this is the bottom surface of your shoe, and this will have atoms, okay, like this. So the cross section, now we are going to find out how many atoms actually are there on the bottom surface of the shoe, because all those atoms are supporting the force. So area of shoe. Now area of one atom or cross-sectional area of one atom will be, and since the atoms are spherical, the cross-section will be a circular one, and if it has a radius of r, the area will be pi r square. Okay, therefore area of an atom is pi into 1.5 into 10 to the power minus 10 square, and this comes 7.07 into 10 to the power minus 20 meter square. Okay, is the area of one atom, and if you divide the area of shoe by area of one atom, you will find the number of atoms present there. Okay, so the number of atoms will be area of shoe divided by area of one atom, and this will be 0.03 divided by 7.07 into 10 to the power minus 20, and this gives 4.24 into 10 to the power 17 atoms. Okay, this is the number of atoms, and these atoms, 4.24 into 10 to the power 17 atoms, these atoms are supporting the force of 400 Newton. So one atom supports a force of, the force supported by one atom will be force supported by shoe divided by number of atoms. Okay, so force supported by shoe divided by number of atoms, 4.24 into 10 to the power 17, and this will be something like this, 9.24 into 10 to the power minus 16 Newton. Okay, so this is the force supported by one atom. Now consider the type of atom present there, and at the bottom of the surface or in the atmosphere, oxygen gases are abundant. Therefore, taking oxygen as the most abundant atom there, an oxygen atom has an atomic number of 8. Okay, so it has 8 protons, therefore 8 electrons, and we can consider for any atom is the nucleus, and in a given time or a given point, if the atom has 8 electrons, 4 electrons will be here and 4 electrons will be there. So this is the, for consider this is one atom of the surface of the floor, and this is another atom of the surface of the bottom surface of your shoe. So 4 electrons and 4 electrons, and we can consider that the force supported by one atom, the force supported by one atom is actually supported by 4 electrons. Okay, so 4 atom, therefore force supported by each electron will be force of atom divided by 4, and you will have 2.36 into 10 to the power minus 16 Newton, force supported by one electron. Okay, and the force that is supported by one electron is actually due to the repulsion between the electrons, and from Coulomb's law we know the force of repulsion is equal to 1 by 4 pi epsilon naught, taking air as since it is considered free space, 1 by 4 pi epsilon naught, and Q1 Q2 divided by r square, and r is the separation between the electrons. Okay, so this is the force, Coulomb force, and here it will be the force of one electron. Okay, now subject r, Q1 Q2 divided by 4 pi, or you can write Q1 Q2, and you have r is r 1 by 4 pi epsilon naught into Q1 Q2 divided by f electron. Okay, and root over. Now you have the value 1 by 4 pi epsilon naught is equal to 8.99 into 10 to the power 9, Q1 and Q2. Q1 and Q2 are charges on electrons. So minus 1.6 into 10 to the power minus 19 Coulomb multiplied by minus 1.6 into 10 to the power minus 19 Coulomb divided by force supported by 1 electron, that is 2.36 into 10 to the power minus 16 Newton, and you'll have about 9.9 into 10 to the power minus 7 meter. That is approximately 1 into 10 to the power minus 6 meter, and that is approximately 1 micrometer. So you are levitating at a height of 1 micrometer from the surface. Okay, and for this repulsive force, actually we can say that no surface, or there will be no contact between two surfaces. Okay, we can feel it, but actually there is a gap between two surfaces in contact, and actually they are not in contact. So this is the R between two electrons, electron. Experimental verification of Coulomb's law. To verify Coulomb's law, we'll require some equipments. For example, this is a bench, and you'll require a torsion balance. Okay, a torsion balance. This is a bench, an insulating rod, and here this is the torsion balance, or it is also called rotating balance. That means you can rotate it. Okay, for example, like this torsion balance, and you can rotate it like this. And this is fixed one. This is a charged sphere, and it is loaded some weight so that it doesn't move. Another charged sphere suspended by thread, and we'll have a ruler placed behind, and this sphere has a pointer here to judge the reading from the scale. Okay. For example, you have, suppose looking from the front, if you have a charged sphere suspended by a thread, another charged sphere suspended by a thread. First consider the two spheres are neutral, okay, and they have weight since they are neutral, and this one two neutral spheres, and they will not repel or attract each other if they are charged, oppositely charged, and then they will repel each other, and because of the repulsion, you see like this, okay. So the position will be, this is the angle theta, deflected angle theta, deflected from the original position, okay. But if you have loaded this one, then the force will not be enough for this one to move, okay, since it is loaded. So the force is not enough to move this loaded sphere, the heavy sphere. So this will be in equilibrium, or this will be at the position it was before it was brought, and repulsion, and it will be then repelled more, okay. This will not, it will move in this direction more. So this is the angle of deviation or angle of deflection, okay. And if you observe this from front, and the front view will look like this, and this is the scalar ruler, sorry, okay, ruler, and this is the pointer, you can judge. This is the torsion balance. Why this is required here? Because using the torsion balance, you can rotate it. So by rotating it in this direction or in this direction, actually you are adjusting the distance, okay, from the two spheres, between the distance between the two spheres. If you rotate it in this direction, you are moving this heavy sphere in this direction. If you are moving or rotating this one in this direction, you are moving it in this direction, okay. So the torsion balance is actually required here to adjust the separation between the two spheres. Now considering the movement of this one, okay, from the front view, a charged sphere or lighter charged sphere that has moved because of the electrostatic repulsion between them, okay. And suppose this is the heavy or loaded sphere which hasn't moved, okay, and there will be a tension along the string T, tension, and this is the weight of the sphere mg acting downwards, and this is the separation between their centers. This is right angles, and this is the distance it has moved from its initial point, or the point it would be without having any charge there, and this is the length of the string, okay, or length of the line, and since it is experiencing a repulsive force, this is the F Coulomb, the force of repulsion on the lighter sphere. And figure 2 actually shows the forces. Figure 2, this second figure I have drawn, second figure shows you the forces acting on the lighter ball, Coulomb force or the electropulsive force, and the weight and the tension on the line. Okay, and by resolving and equating the horizontal vertical components of the tension, we can develop a method. For example, in this case, since it is tension, and suppose this is the angle theta. Okay, so the tension will have two components there. If it is tension having an angle theta, so the tension will have two components. This one is T cos theta and this one is T sin theta. And we can see that the horizontal component of the tension is balancing the Coulomb force. Okay. Horizontal component of the tension T sin theta is balancing the Coulomb force. So we can write F Coulomb is equal to T sin theta. And the vertical component of the tension T cos theta is the vertical component of the tension T cos theta is balancing the weight. So we can write mg is equal to T cos theta. Okay, if you divide equation 1 by 2, dividing equation 1 by 2, you'll get F Coulomb divided by mg is equal to T sin theta by T cos theta. Cancel T, then F Coulomb will be, or F Coulomb divided by mg will be tan theta. And look at the diagram. Tan theta, for theta this is the adjacent, for theta this is the opposite and this is the adjacent. And for a small angle, we can write tan theta is equal to opposite by adjacent, so D divided by L. And using this here, F Coulomb divided by mg will be D divided by L. Now F Coulomb will be mgd divided by L. Now K Q1 Q2 divided by R square. Q1 and Q2 are the charges on the spheres. Q1 Q2 divided by R square will be mgd by L. And now subjecting 1 by R square equal to mg k q1 q2 into L into D. Okay, and if you vary the R, you will find out that D will also vary. Okay, and considering it with y is equal to mx. Okay, y, this is y 1 by R square, and this is x D. So if you vary R, you will have 1 by R square, and for different R you can measure the d, a distance moved by the lighter sphere from its original position. And then if you draw a graph of 1 by r square against d, the graph will be a straight line. If the graph is a straight line, it is supporting the Coulomb's law. So Coulomb's law is therefore then verified. And the gradient of the graph 1 by r square against d will give you mg divided by k q1 q2 into L. Okay. So if 1 by r square against d is a straight line passing through the origin, the law is verified. This is the verification of, or experimental verification of, Coulomb's law. Now the last part of the chapter, Millikan soil drop experiment. Okay, so before understanding Millikan soil drop experiment, I have to draw the diagram required for understanding this. Without drawing the diagram, you won't be able to understand what Millikan did to find the charge on an electron. His experimental setup was like this. I'm drawing a simplified version of his experimental setup. Variable PD, or potential difference, variable PD, this one is positive and negative terminal. So this is the negative terminal and this is the positive terminal. This is the cathode and this is the anode. A container of oil, this is a viewing microscope, and there was a light source here. This is the vaporizer, oil there, and this is the cathode and this one is the anode. When it's screwed, so what Millikan did to find out the charge on an electron, before going to understand that, you must know that when oil is vaporized or when oil is scooted through the vaporizer, okay, when oil is scooted, the oil droplet gains negative, oil droplets gain negative charge due to friction with the nozzle of the vaporizer. Okay, when oil is scooted, the oil droplet first. Remember, when oil is scooted through the vaporizer, the oil droplets become negatively charged. That means they are gaining electrons. When something becomes positively charged, it loses electrons, and when something becomes negatively charged, it gains electrons. So the oil droplets are charged due to friction with the nozzle of the vaporizer. Okay, and Millikan first did the experiment with the electric field turned on, or with the electric field switching on the supply. When the electric field is turned on, and you know that the oil droplets have mass, and because of gravity they will fall downwards, and by adjusting the electric field, I have another thing here, the distance between the electric plate, the distance between the anode and cathode D. So by adjusting the variable PD, you can adjust the electric field strength, and we know E is equal to V divided by D for uniform electric field. Since the plates are parallel, there will be a uniform electric field, the field line like this. Okay, electric field line. So by adjusting the V or potential difference, you can adjust the electric field strength, and adjusting the electric field strength, you are adjusting the electric force, and we know F is equal to EQ. Okay, so by adjusting the force, Millikan maintain the oil droplet stationary, or Millikan make sure the oil droplets are held stationary there, and this is because of the electrostatic repulsion from this, because this is negatively charged and the oil droplets are also negatively charged and like charges repel. So in that case, we can consider that the weight of the oil droplet, or the weight of an oil droplet, is balanced by the electric force, since the oil droplets are held stationary there. And Millikan did the experiment with the same apparatus, using the same apparatus without applying any electric field, by switching off the circuit. Okay, in that case, Millikan let the oil droplet to fall, and since the chamber or the apparatus, the inside the apparatus is full of air, the oil droplet and the oil droplets are very light. Due to viscous drag, the oil droplet will reach terminal velocity, and by using with the aid of the viewing microscope and the light source, Millikan was able to find out the terminal velocity reached by the oil droplet, and in that case we can say that the weight is balanced by viscous drag, or the Stokes force. We can ignore the air upthrust there, because since here the density of air is negligible, you can ignore the upthrust. So in that case, when the oil droplet reaches terminal velocity, we can consider ignore, because when the oil droplet is falling downwards, the downward force is mg. Okay, wait, and since if there was upthrust, the upthrust will be upward, and since it is falling downward, the viscous drag will be in upward direction. But since air is very less dense compared to the oil, we can ignore the upthrust since it is very insignificant. So in that case, we can consider that the weight is balanced by the viscous drag. And Millikan also did another experiment. Millikan finally did the experiment or repeat the experiment by altering the sign of the charge or the terminal or polarity of the electric field, and made the oil droplets being repelled upwards and reaching upward terminal velocity. Okay, so now if we consider the first one and the second one, we will be able to find out the charge on the electron. Okay. When you first, if you turn off the switch or if you don't apply any electric field, the oil droplets will reach terminal velocity, and ignoring the air resistance, we have already discussed that if you ignore the air resistance, if you ignore the upthrust, not air resistance, if you ignore the upthrust, we can write that when without any electric field applied, okay, without any electric field applied, the oil droplets having weight in downward direction, and since it is reaching terminal velocity, there will be viscous drag. Okay, so in this case, the circuit is switched off and the oil droplets are allowed to reach terminal velocity while flowing through the air, and in this case we can write that mg, the weight of an oil droplet, will be balanced by viscous drag, which has the formula 6 pi r eta v term. And with the aid of the beam microscope, Millikan was able to find out the terminal velocity of the oil droplet, first one. And when you apply the electric field, in this case there was no electric field, the oil droplet falls due to gravity, and the weight was balanced by the viscous drag since upthrust is ignored. So with electric field applied, okay, with electric field applied, Millikan made the oil droplets to be held stationary. So since the bottom part of the plate, or the bottom plate, is negatively charged, the oil droplets are also negatively charged, and the bottom plate will repel the oil droplets, and by adjusting the variable PD, Millikan adjusted the electric field strength there. That's how he actually adjusted the force on the oil droplet and make sure that the oil droplets are stationary, held stationary. In that case, we can write mg is equal to electric force. Okay, and in case of electric force, you can write electric field strength into Q. Q is the charge on, we are considering Q the charge on an oil drop, and we know that E is V by D. Okay, so equation 1, equation 2, and equating these two, we can write VQ divided by D is equal to 6 pi from equation 1 and equation 2. We get 6 pi eta V term is equal to VQ by D. So our VQ by D is equal to 6 pi r eta V term. 6 pi. This V is the potential difference, and this V term is the terminal velocity, and r is the radius of the oil drop. And you'll be surprised how Millikan measured the radius of the oil drop, since it is very small and it's difficult. Actually, it's impossible. It was impossible for him to measure the radius of the oil drop then. So we have to replace r from in this equation, and let's subject the q, the charge on a oil drop. This is the charge on an oil drop. Q will be 6 pi r eta v term divided by v, which is the potential difference between the plates. Okay, now 6 pi eta v term, potential difference v into r. Why r is separated? Because he couldn't find out r, so we have to do something to measure r or to find the value of r in a different way. Okay, since we have measured the terminal velocity, we have another formula of the terminal velocity, and we know that v term is equal to 2r squared g rho oil minus rho air divided by 9 eta. And since we are considering air is very less dense and we are ignoring the density of the air, and that's why we ignored the upthrust, we can cancel or remove the density of air. So we have the formula v term is equal to 2r square g rho oil, density of oil, divided by 9 eta, viscosity of air, and subject r from this equation. We have 9 eta v term divided by twice g rho oil to the power half, since it is r squared there. And if you put the value r in this case, and you will have the formula finally q 6 pi eta v term divided by pd, potential difference, into 9 eta v term divided by twice g rho oil to the power half. Look at the equation. 6 pi eta, the viscosity of the air, 6 pi constant, v term terminal velocity can be measured, v potential difference you have applied when you held the oil drop stationary, 9 it again constant, v term measured, twice g constant, rho oil, density of the oil known. And using this equation you can find out the charge on an oil drop. And Millikan did the experiment several hundred times, and he found out that q is actually a whole number multiple of 1.59 into 10 to the power minus 19. So q, and doing the experiment several hundred times, he found out that q is a whole number multiple of 1.59 into 10 to the power minus 19. This is the charge on an electron, because the oil drop becomes charged by losing some number of electrons, or by gaining some number of electrons. And he found out that since the charge is a multiple of this number, this is the smallest value of the charge, and this is the charge contained by one electron. Okay, this is how Millikan found out the charge on an electron, and this value is actually only 1% less of the value accepted today. Okay, this is the Millikan's oil drop experiment. I hope you find it useful. Okay, Allah Hafiz, see you soon.